Hi everybody, today I'm going to be talking about net change. So in order to understand net change, you must first understand that the integral from a to b of a function f of x dx is equal to the area underneath a curve f of x from points a to point b. So now that represents this whole area right here. Now, before, when we were trying to find this area, we had to use a bunch of little rectangles, use the summation formula, and it was a whole big process that was really easy to mess up. But I'm going to show you a much easier way to do it now. So we're going to look at the velocity function. So we're going to have a velocity function, we're going to set it equal to 5 miles per hour. And now, once we have this, we can draw that out. So 5 miles, and we're going to draw it across right here. And we're going to go from point A to point B, and we'll set that equal to 0 miles, and this, or 0 hours, and then we're going to set this equal to 5 hours. So now, when we take this, we want to find the area underneath here. So since this is 5 and this is 5, it's a simple rectangle, we're able to just multiply that, and we're going to get 25. Now that we have 25, we don't know the units. So we look at it and we have 5 miles per hour. So that's this right here. So we're multiplying 5 miles per hour by 5 hours. So when we multiply it by 5 hours, this cancels out with this. So now you get 25 miles. Now that you've got 25 miles, you've got the value and you've got the units. You just don't know what it represents. So since we can draw this out as 0 to 5, the integral of dt dt, it has to do something with the antiderivatives. So we can look at s of t, and using the velocity function, we can gather that it will be 5t plus c. So if we look at this, we want to see how much it was displaced during 0 to 5. And we look at this, s of 5 minus s of 0. When you do that, you're going to get the displacement, because you're going to figure out where it ended, where it started, and the distance it traveled between them. So once you figure that out, you just plug it in. So you're going to get 5 times 5 plus c minus 5 times 0 plus c, and that's going to equal 25 plus c minus 0 minus c. So the c's are going to cancel out and you're just going to get 25 miles. Now if you can remember, the answer to the area underneath the curve was 25 miles. So s of 5 minus s of 0 is equal to derivative from 0 to 5 velocity dt. So now this doesn't only work for velocity functions when it's in a straight line. This works for every single equation that you're going to get for a function. So now we can do a little practice with this. Go over, let's see, we'll go with 0 to 3 for x squared dx. Now when we look at this, looks a little something like that. So we're going to go from here to here. We want to find this area. So we need to find the antiderivative in order to be able to plug it in. So the antiderivative is going to be x cubed over 3. Now in the other example that I showed you, the c's canceled out, so we don't have to worry about that when we're doing a definite integral. So now we're going from 0 to 3. So we're going to plug in 3 and we're going to subtract the plugged in 0 from that, because we're subtracting the beginning from the ending. So we're going to plug in and we're going to get 3 cubed over 3 minus 0 cubed over 3, and that's going to equal 9. So the area under this is just equal to 9. It's much simpler than using the whole summation formula and everything. So now with even functions, we'll give you the function -2 to 2 of absolute value of x dx. So when we're going through this, we can see by the graph that it looks a little something like that, right here and right here. So these both are going to be equal because it's the same on both sides. So we can split this up because this has to be a piecewise function. We can't take the antiderivative of with an absolute value. So we go -2 to 0 of negative x dx plus 0 to 2 of x dx. Now both of these added up are going to be equal to this. But what we also know from right here, that it's an even function, that this is going to be equal to this. So we can just take one of them, and I'm going to use this one because it's much cleaner. There are no negatives to deal with. And you multiply it by 2 and you can get this value. So we'll do 2 times 0 to x dx, and you plug that in, you're going to get x squared over 2. And don't forget, you have to multiply that all by 2, and it's going from 0 to 2. And that's going to equal 2 times 4 over 2 minus 0 over 2. Now that is going to simplify out to 4 over 2 times 2, cross those out, and the area is 4. Now with an odd function, you look at it, and we'll go with x cubed. So right here and right here, we'll go with -2 to 2 again. -2 and 2 of x cubed. So now we can see that since this is the same as this, but negative because it's below the x-axis, what we can do is separate this out. So this is -2 to 0 of x cubed dx plus 0 to 2 of x cubed dx. This is equal to the negative of this. So since these are opposites, when you add them together, they're just going to equal 0. So if it's an odd function and you're going from -a to a, you're going to get 0, no matter what it is. So these are the basics of calculating net change. Thank you for listening, and I'll see you guys later.